Okay. My chair just went, so I guess it's a good time to start. Cool. So, yeah, I'm John Wright. Today I'll tell you a little bit about the random purification channel, and I just wanted to say, oh wait, is this animating or not animating? Let's see. Hold on. Okay, that's animating. All right. Yeah. So I just wanted to say, begin by saying, welcome to the channel. Sorry, not the channel. Welcome to the workshop. This is a workshop on this random purification channel. It's a new tool in quantum information for studying mixed quantum states. Now I see most people in the audience are like quantum aficionados, but if anyone here is not, we're just going to assume like light knowledge, at least for today, of quantum computing. So things just like pure states, mixed states, the basic formalism of quantum mechanics. If you're familiar with that, then you should have no problem today. The outline of well, my talk is I'm going to begin by just saying what is the random purification channel. In the second part, we're going to show two separate constructions of the random purification channel. Then I'm going to say a little bit about the history of the random purification channel, and then I'll conclude by talking about the workshop and give you kind of the outline in the next few days. So to begin, let's talk about what is a random purification channel. And to start with, I have to first define what a purification is, and that entails first talking about bipartite quantum states. So let me just remind you some of the formalism of bipartite quantum states. So let's say we have two quantum particles in a joint state, so they're entangled. I'm going to refer to the first subsystem as subsystem A, the second one as B. And let me write psi AB for the joint state on both particles. So a classic example of a bipartite state that we probably all know and love is the EPR state, which is 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. And it turns out that any bipartite quantum state will look something like this EPR state. So some superposition of like a 0, 0 and a 1, 1, or something that looks something like that. And this form that applies to general states is known as the Schmidt decomposition. And the Schmidt decomposition of a state psi AB is just given by the sum over I equals 1 to R of square root alpha I times ket ui on the A register and ket vi on the B register. So what are these objects on the right here? So R here, it's known as the Schmidt rank of the quantum state. So just how many terms are in the sum. The vectors on the A side, U1, U2, and so on, are just some orthonormal basis for the A subsystem. And similarly, the VIs are just some orthonormal basis for the B subsystem. And then finally, the alpha i's, these are known as the Schmidt coefficients of the state. They're non-negative and they sum to 1. And a fact is that if I take my bipartite state and I just look at the A part of it, so what is the subsystem of my state on the A particle, then what I'm going to get is a mixed state called psi sub A. And we can define it, describe it very easily in terms of the Schmidt decomposition. So it's just going to be the sum from I equals 1 to R of alpha I times the ui. And note that if psi AB has Schmidt rank R, then this mixed state psi sub A will have rank R. Similarly, if we look at the mixed state on the B subsystem, we'll get psi B. And that's going to be the sum from I equals 1 to R, alpha I times the VI vector. And note that like psi sub A and psi sub B, they're different states. They're sitting on different registers. They may have different dimensions. But one thing that they share in common is that they have the same spectra. So they have the same set of eigenvalues, the alpha i's. Okay, so that's a bipartite quantum state. Now, what is a purification? Well, let's suppose we have some mixed state rho, d by d mixed state. So just sitting there in space. Then a purification rho of rho is just any pure state, psi sub AB, such that if you only look at the first register, psi sub A, you get back rho. So pictorially, if rho is sitting there and we call it subsystem A, now we imagine extending the system by adding another register B. And then psi AB is going to be the joint state on both systems. And if I just look at the first system and get back rho, then what I have is a purification. So now using all the math we developed on the last slide, suppose rho has a spectral decomposition, sum over I, alpha I times ui. Then the Schmidt decomposition of psi AB, it can be any state of the form psi AB equals sum over I, square root alpha I times ui vi. Because, we saw on the last slide, if we throw out the B register, we'll get back rho. So let me note a couple things about this. The VIs, they can be any orthonormal vectors here. It doesn't matter what they are. You will always get a purification of rho. And so that does mean that we can take the B subsystem and rotate it freely, and we will always maintain the property that it's a purification. Another thing to note here is that if rho is rank R, then actually we only need R vectors in the purification. So, if we replace D by R here, that D gets replaced by R here. And for this to work, the only property that we need is that there are orthonormal VIs, and we can always do that in a dimension R space. And so that means if we want, we can always assume that the dimension of the B register is at most R. Okay. I may also sometimes refer to these VIs as the purifying vectors. There's this philosophy in quantum mechanics. Okay, so yeah, why are purifications useful? So there's this philosophy in quantum mechanics that you see a lot. It's sometimes called the Church of the Larger Hilbert Space. It was coined by John Smolin. And it's just the philosophy that it's often convenient to analyze mixed states by actually considering purifications. So sometimes for some problems, it's just much easier to solve the pure state version. It's much easier to reason about pure states. And other times, purifying actually gives you some genuine new insight about the structure of your problem that you wouldn't have if you were looking at the mixed state version. So two examples of this philosophy in action, one of them in the area of quantum query complexity. There's this well-known method of ambinus known as the adversary method that helps you characterize the query complexity of some problems. And if you look at Ambinus's original paper, what he did was he took like the query scenario, which somehow corresponds to a mixed state, and then he considered a purification of it, and he got the Ambinus, the adversary method. Another example of this in the quantum query complexity literature, a much more explicit example of this is the compressed oracle method of Chandry, which again helps you understand query complexity by using purifications. So one question you can ask is, can this Church of the Larger Hilbert space be made operational? So not something that you just do in your analysis, but can you actually make an algorithmic version of it? And in the context of this talk, what that means is there a quantum channel which maps a mixed state to one of its purifications? And I would say prior to this line of work, you might think that actually the evidence seems to be no. And let me give you just a very small argument why it might be no. So perhaps purifying these mixed states is actually hard. And let me show you this by proving the following fact, that there does not actually exist a quantum channel phi, which maps each mixed state rho to a fixed deterministic purification ket rho. So meaning whenever I plug in rho, I always only get one purification back. And so let me prove this to you. So assume for sake of contradiction that there does exist such a phi. So what that means is I take phi, I plug in rho, and I get back ket rho. And now let me imagine applying the same channel to a different state sigma. So I take phi, I apply it to sigma, and I get back ket sigma. So now what I'm going to do is I'm just going to imagine applying phi to the mixture of rho and sigma. So phi applied to 1/2 times rho plus 1/2 times sigma. And by linearity of quantum mechanics, this is the same thing as applying, as getting 1/2 times phi of rho, which is just rho, plus, which is ket rho, plus 1/2 times phi of sigma, which is ket sigma. So you get 1/2 ket rho plus 1/2 ket sigma by linearity. But you remember, the thing here on the right-hand side, it's a mixed state. And what we're supposed to get, the thing on the left-hand side is a mixed state. What we're supposed to get on the right-hand side is a pure state. but that is not pure. That's a mixed state. And so this is a contradiction. And there is some follow-up work by Liu et al., or some work by Liu et al. That's very recently, came out recently, which if you are interested in this problem of producing one fixed purification of your mixed state, then you can do it, but it actually requires many, many, many copies of your original mixed state. So if rho is a d-dimensional mixed state, you require at least d copies of rho to even approximate just a single fixed purification, which is very expensive. Okay, but again, note here that we have this assumption that our channel is always mapping us to a single fixed deterministic purification. And so it naturally begs the question of what if I allow my channel to output random purifications? And if you do that, you get this random purification channel. So this was introduced in a recent work of myself, Ewan Tang, and Mark Jandry. And what we showed is that there exists a channel called Purify R that takes in n copies of a rank R mixed state rho and acts as follows. So when you look at Purify R applied to n copies of rho, what it's going to give you is the expectation over ket rho of ket rho tensor n. And what is ket rho? Well, it's going to be a random purification of rho in which the purifying register B has dimension R. So this does tell you actually that you can purify so long as you allow your purification to be random. And not only that, we showed that it can be implemented in diamond distance delta in polynomial time, so in poly n log d log 1 over delta, which is basically the runtime that you would hope for this problem. Okay, so 3 notes on this. I think this shows, like, once again, the surprising power of randomness in computer science. It takes something you couldn't do without randomness, and then you can do it with randomness. Let me say a little bit, what does this random purification actually mean? So let's suppose rho is this state right here, sum over I alpha I times ket u. Then we saw a purification of it is going to be a state ket rho AB, sum over I root alpha I times ui vi. And what it means for this to be a random purification is just that the vi's, v1 through vr, are a Haar random basis within B. Okay, so they're just chosen to be orthonormal and then Haar random. And the last thing I want to note, which is very important, is that the purification, you get n copies, and the purification is consistent across all n copies, okay? So it's not just like n independent purifications, it's n copies of the same purification, which will be important for applications. So this channel came out less than a year ago, and already we've seen applications of it to many different areas. So let me just show you these. It's been applied to problems in quantum state learning, problems in quantum state testing, problems in quantum state metrology, problems in quantum state channel learning, in quantum query complexity, quantum Shannon theory, some problems where you're doing state transformations or quantum states. Finally, there's kind of like an independent work that applied something very similar to the random purification channel in quantum crypto. And we're going to see many of these applications later in the workshop, so I'm not going to talk about them in this talk. But I do want to demonstrate why the random purification is nice. So what I'd like to do is just show you 2 cute applications of the random purification channel right off the bat. Okay, so cute application number 1 that I'll show you is the following. So for many tasks in quantum learning, your input is going to be n copies of some mixed state rho. You're given rho as a mixed state, you want to learn some property of rho. And a natural question that's come up here and there is, suppose instead of given n copies of the mixed state, you're given n copies of rho AB, which is a purification of rho. This is, a stronger resource than rho, because given a purification, I can always recover rho just by tracing out the B register. Okay, so I can always do more with the purification, or at least as much with the purification as I can with the original state. But then a natural question is, does this ever actually help? Is it ever actually better for you to be given a purification rho? And we get a very simple answer from the random purification channel. The answer is no, because just given rho tensor n myself, I can create my own purifications of the state by applying the random purification channel to it. So this application number one, I'm going to call this like the purifications don't help application, and we'll revisit it a little bit later in the talk when I talk about the history of the random purification channel. Um, this was originally proven by Chen and Wang and Zheng in 24. But now I think it has a very nice, simple, clean proof using the random purification channel. Or very simple, it follows very directly from the random purification channel. All right, the second application, it applies to a problem called spectrum estimation. So in spectrum estimation, you're given n copies of a mixed state rho. And your output here is an estimate of the eigenvalues of rho. So an estimate alpha hat, which should be close to alpha, rho's eigenvalues. And in this application, it's going to be so this application is the following fact, which I learned, it's due to Nora Tan. Let's suppose you have an algorithm which solves spectrum estimation with n equals f of d copies of rho, where here d is the dimension of rho. Then it turns out if rho is rank R, you don't need f of d copies, you only need f of r copies. So, you know, if R is small, then you can get a significant amount of savings. So that's the fact. And let me show you the proof of this. So the proof is, we'll just take your rank R state, take the n copies, and apply the random purification channel to it. And let psi a b tensor n be the result. So now note, so this is a purification of rho. The dimension of the A register, because that's the dimension of our starting register, that's going to be D. But because rho is rank R and we applied purify R to it, the dimension of the B register isn't going to be D. It's going to be much smaller. It's going to be R. So now what we should do is we should just take psi AB and trace out the A registers, our starting register, just discard them. And what we'll be left with is n copies of psi B. And what is psi B? Well, this is, it lives inside B, so it's a dimension R state, but it's going to have the exact same eigenvalues as rho does. Because remember, in a bipartite state, the B register has the same eigenvalues as the A register, and the A register in this case is just equal to rho. Okay, so if I want to learn the spectrum of rho, it suffices to learn the spectrum of psi B. And so now I can just run my spectrum learning algorithm on psi B with f of r copies instead of f of d. And that's a proof. So this is something that like we've observed that algorithms in spectrum estimation, they always satisfied this property. But somehow we never had like a clear operational reason why. And now we do. If you're interested in this, Nora, she has a paper exploring this sort of stuff. So with this and then other related things with Angus Lowe, which will be hopefully appearing on the archive tonight. All right, so that's it for the random purification channel. We saw the definition and some applications. And now I'd like to move on to explain how do you actually construct the random purification channel. There are actually at least two methods I know of constructing the random purification channel. I mean, they both give the same channel, but two different ways of arriving at the channel. Method number one, I'll call it the Fourier basis method. It's the original construction that we did in this paper with Ewan Tang and Mark Chandry. And one nice thing about this algorithm, or this method, is that when you write it down, it just very clearly gives an efficient algorithm for the channel. Method two, I'll call it the standard basis method, because you don't really need to use much Fourier analysis. It's a second construction. It's due to Girardi, Anamele, and Lamy, not too long after the original paper. It's like a super slick construction, and I'd say in the future, probably just the right way of defining the channel. But one downside, I think, of this method is that it's non-algorithmic. It doesn't really suggest an algorithm to use. So probably the right way of thinking about these two methods is like one of them is the right way just to state the channel, and then the other way is a way that you would say if you want to actually implement the channel. And I think in applications, both methods have their pros and cons occasionally. So let me start with method number 1, the Fourier basis method. And I'm not going to tell you the entire thing. I'll just give you a simple example of how it works in the case of just one copy. So let's look at the purify channel when we only have one copy of rho and we want to output one copy of a purification. So to start with, let's suppose rho has this eigen decomposition, sum over I, alpha I times ket ui. And then we saw that this purification rho AB, it's going to be the sum over I of root alpha I, ui vi, where these vi's are going to be Haar random vectors. So, our goal is to compute this state, the expectation over ket rho of ket rho, the expectation over a random purifying vector. So let me just expand this, do some calculations, and see what I get. So when I expand it, what I'm going to get is expectation over rho, sum over I, root alpha I, ui vi, times sum over j, root alpha j, uj vj. Now what I'm going to do is pull those sums out and then move the expectation on the inside. And then what I'll get is, sum over ij, root alpha j, times ui uj, tensored with, and now the expectation over vi of vi vj. Because remember, in this expectation over the random purification channel, or sorry, over a random purification, the only thing that's actually being averaged over is the random state in the purifying register. So now if we look at this, what's going on here? Well, it breaks into two cases. So if I is equal to j, then it's just vi. That's just going to be a random rank 1 vector in your r-dimensional space. And so if I take a random rank 1 vector and I average over it, what you just get is the maximally mixed state, identity over R. On the other hand, if I is not equal to j, then you just have two orthonormal vectors, and you're taking the expectation of their outer product, and that's just going to be 0 when I is not equal to j. And so this sum, it just collapses to the sum over I of alpha I times ket bra ui, tensored with the maximally mixed state. And that first sum, of course, is just equal to rho, the starting state rho. So if I want to compute this purification, it turns out to suffice to just take rho and append a maximally mixed state on the B register. It's very simple. Now, of course, that's for one copy. Doing the case for general N, it involves some representation theory, but I would say not a lot. I mean, I've written many representation theory proofs in my life. This is one of the simplest ones. And if you know representation theory and you know you're supposed to prove that this channel exists, then you can just follow your nose and the calculations are not too hard. But feel free to ask later if you're interested more in this, and I'm happy to explain how it works. Okay, so that's all I want to say about the Fourier basis method. Now let me move on to method 2, the standard basis method, this one that came from Girardi, Anomele, and Lamy. So in this method, let me just start by considering this one matrix I, which is the sum over I equals 1 to d of ket bra I, aka just the identity matrix. And what I'm going to do is actually do something a little funny, which is consider ket I AB, which is a random purification of the identity matrix. So in other words, that's going to be the sum over I of ket I tensored with wi, where w1 through wd are themselves our Haar random vectors. And in this standard basis method, what you're going to do is start by considering this matrix right here. I'll call it Rn. And it's just the expectation over a random purification of the identity matrix of ket I tensor n. So this is like what the channel should output if you plug in identity tensor n. Okay, and with that stated, it's very simple to state actually what does this channel do. Purify, what it's going to do is take in the state, hopefully n copies of rho. It's going to, right here, I don't know if you can see, yeah, there we go. It's going to append on the B register the identity matrix, and then it's just going to sandwich it by square root Rn. Okay, So you append identity, you sandwich it, and that's it. So that's the channel. And yeah, that's one reason I like it. You can just write it down. It's very simple, very clean. It's not obvious why it purifies, though. So what I'm going to do is just spend a few slides going through the calculations of why this is indeed carrying out the random purification channel. And this will, yeah, so I'll have to prove like a couple of very natural facts. And then once you have those facts, like it'll be an extremely slick proof. So to begin with, let me just note something about the distribution over this random purification of the identity matrix. So let me take W, which is a Haar random matrix. And let's look at this IAB, which again, it's equal to sum over I of ket WI. Then I claim this has the same distribution as this vector. It's sum over I of ket I times with the Haar random matrix W applied to the B register. And that's because, if we apply W to the B register, then this ket I is just going to become a WI. And now, what is this here? We have an EPR state with a matrix applied to the B register. And the EPR state has this property that's sometimes called the ricochet property, which is if I apply a matrix to the B register, that's the same thing as applying the transpose of that matrix to the A register. So this is equal to W transpose applied to the A register of the EPR state. And you remember, W is Haar random. So it's basically like I can take an EPR state and then apply a Haar random matrix to the first register. Okay, and so let's say we took any fixed unitary U on the A register. Then I claim this tells us that IAB has the same distribution as IAB if you then multiply it by U. Because for this state right here, it's like we multiply it by a fixed U, but then that's going to get multiplied by a Haar random unitary anyway. So this unitary is just going to get like sucked into that Haar random unitary, and then you'll still just have a Haar random unitary. So these two will have the same distribution. Okay, so let's just keep that note in mind. All right, so again, this is what we want to prove, that the purify channel is this. And the one little fact I'm going to now prove to you is that this Rn matrix has a very nice property that it commutes with rho tensor n. So rho tensor n times Rn is equal to Rn times rho tensor n. So let me show you why this is the case. And again, once we have this, we can show that the purify channel works. So let's recall this thing that we saw from the last slide. For any unitary U, IAB and then UA times IAB have the same distribution. So let's look at this Rn matrix, the expectation over IAB of IAB tensor n. And because of the above fact, this is exactly the same as the expectation of UA times IAB tensor n, because those two states have the same distribution. Now what I'm going to do is I'm going to pull out the UAs. And what I'm going to get is that this is equal to UA tensor n times the expectation of IAB tensor n times UA dagger tensor n. And that, of course, is just in the middle, that's Rn again. So that's equal to UA tensor n, Rn times UA tensor n. So I can take Rn, then rotate it by the UA tensor n, and I get back the same matrix. And if I rewrite this, if I multiply both sides by UA tensor n, I'm going to get Rn times UA tensor n, which is equal to UA tensor n times Rn. And so what does this say right here? It says that, okay, maybe Rn, the Rn matrix will commute with any unitary UA tensor n. Well, we wanted the exact same statement, except instead of unitaries, we wanted states. We wanted it to commute with rho tensor n. And it turns out, I won't say anymore, but it's a fact from representation theory, that once you commute with all the unitaries tensor n, you also commute with all the states tensor n. Okay, it kind of looks similar. Okay, so that's the proof of that. All right, so now let me use this fact to show that the purify channel works. We want to apply the purify channel to rho tensor n. And that's equal to, rho tensor n sandwiched by square root of Rn. And And now what I'm going to do is I'm going to take rho tensor n, and I'm just going to split it up into 2 square roots. So that's equal to rho tensor n square root times rho tensor n square root. And now, remember that Rn commutes with rho tensor n. And if a matrix A and a matrix B commute, then their square roots commute as well. So what I'm going to do is I'm going to commute the rho tensor n past the Rn. I'm going to do the same thing here. I'm going to commute this rho tensor n past Rn. And now you get the 2 root Rn's in the middle and the rho tensor n's on the outside. And now I can just take those Rn's and I can combine them, those 2 square roots, and I can just combine them into rho n, or Rn. All right. Now this rho tensor n, 1/2, that's just the same thing as, Rn, by our definition, it's just, the expectation of ket IAB tensor n. And then the final little thing that I'll do is I'll just exchange the tensor product and the 1/2. So rho tensor n to the 1/2 is just the same thing as rho to the 1/2 tensor n. And now that I have a tensor n here, I can just move it into this tensor n. And I get that this is just equal to the expectation over ket IAB of rho a to the 1/2 times IAB tensor n. Okay. So very simple manipulations. You square root, you commute, you move to the inside, and then you expand. Okay, so what is this thing right here? Well, now we just have to write down the formulas for rho A, for IAB, and then everything is going to follow. And just to make my life a little bit simpler, I'm going to assume that rho is diagonal in the standard basis. So let's assume that rho is the sum over I of alpha I times ket I, ket bra I. This turns out to be without loss of generality. Then rho to the 1/2, well, it's the same matrix, except where I take the square roots of all the alpha i's. So it's sum over I, alpha I to the 1/2 times ket bra I. And recall from before that ket IAB is sum over I of ket WI, where the WI's are random. So if we just look at their product, rho to the 1/2 times IAB, what we get is, sum over I, alpha I, times ket bra I, applied to the A register, times sum over I of ket WI. And what this is going to do is it's going to look at the A register, and whenever you see a ket I, you're going to multiply it by square root of alpha I. So you're going to get sum over I square root alpha I times ket WI. And that is none other than rho AB. That's a random purification of rho. And so that's the proof. Okay. So very, very simple, very clean. And yeah, so that means that what we have here, tensor n, is just going to be n copies of rho AB. Any questions about that? Okay. One thing I really like about this way of writing down the purified channel is it reminds me a lot of this approximate cloning map. This is like, okay, so cloning, it's a thing, in quantum mechanics, you're not supposed to be able to take like rho and then get rho tensor n, or rho tensor 2, or let's say psi and get psi tensor 2. But it turns out that if you have n copies of psi, of a pure state, you can use them to approximately generate n copies, or n plus k copies of psi. So that's the approximate cloning map. It's due to Werner in '98. And it's just like one of those classic channels that you learn about in quantum information. And what Werner showed is that the approximate cloning map has this form. Right here, you take the input, and then you tensor on identity, tensor k, and then you sandwich it on both sides by this matrix pi sim. If you don't know what that is, that's okay. It's a projector on the symmetric subspace. And then in this case, you have to multiply by some other number to reweight it. But essentially, it's like a very, very similar thing, right? You tensor with some identity, and then you sandwich by the appropriate matrix. And the only difference between the way these channels look is like what are you tensoring on, and then what are you sandwiching? But yeah, I just find this very nice. I like that this is looks very similar to this classic channel. And there's like a nice reason for this, which is that both are actually instances of something called a Petz recovery map. So a more general family of quantum channels. All right, so that's the 2 constructions of the random purification channel. And now, what I want to do a little bit is say, where did this channel come from? How did we come up with it? And so I want to tell you a little bit about the history of this channel. And I think of this channel as combining kind of two streams of research. One of them is stream number one, these purifications don't help lemmas that I mentioned earlier. And then stream number two, which is something a little more recent that we've been calling the acorn trick. And I'd like to tell you just a little bit about each of these. Okay, so for stream number one, let's start with that. And that, at least for me, when I got started with this, was when I was a postdoc at the MIT Center for Theoretical Physics back in 2017. So back then, I was like chatting with Mehdi Soleimanifar, who was a PhD student. And we were like working on some problem involving matrix product states. We wanted to understand like how easy is it to test if a state is a matrix product state. And at this point in the project, we were trying to prove lower bounds. We wanted to show that it was actually hard. So we had a conversation something like this. Like we realized, okay, let psi AB be a bipartite quantum state. And it turned out that the thing we wanted to prove boiled down to just understanding the following questions. How many copies of psi do you need to test if it has Schmidt rank R or not? So does my state have low Schmidt rank, or is it far from having low Schmidt rank? And when I asked this question, Mehdi, it seemed clear, to him that the best algorithm that you should do, the Schmidt rank, it's kind of invariant under rotating both the A and the B subsystems. So for some reason, it just seemed like the best algorithm should just discard the B subsystem. And if you do that, then what you're left with is just copies of psi A. And psi A, it has rank R if and only if the original ket psi has Schmidt rank R. So it just boiled down to understanding how many copies were needed to test if psi A had rank R or not. And for this, I was like, yes, I do know this actually. This is work of myself and Ryan, and we showed that this requires at least R copies of the state. So that seemed promising, but then Mehdi pointed out, how do we actually know that the best algorithm should discard B? Maybe the best algorithm could use a purifying register somehow. So we thought about it for a bit, eventually proved what we wanted, and then took us a few years to actually write it down. But so in our 2022 work, we showed, suppose you're trying to test some property of psi AB Schmidt coefficients. So just of the Schmidt coefficients, for example, the rank. Then what we showed was that the best algorithm does just discard B and then tests psi A spectrum instead. In other words, this tells you that purifications don't help, at least when you're testing properties of psi A, rho equals psi A spectrum. Because if it did help, then you wouldn't just discard B, you would actually use psi AB. Now, when we originally proved this, we kind of thought, well, this must be folklore, right? Must be in the literature. Mehdi was like, yeah, it definitely feels like it. We went to Aram, and he was like, yeah, probably, or maybe definitely folklore. Just the sort of thing that anyone who works in this area probably knows and knows how to prove it. We spent some time looking for references and could not find papers, but it's a large literature. There's a lot of old papers that we didn't know about. So when we wrote this paper, we kind of didn't call attention to this, and we just let it be like a random lemma on page 25. But I kind of, personally, I wish we hadn't. I wish we had called more attention to it. It's been missed by a lot of people. It's been accidentally reproven at least once, and so on. So there's a part of me that wishes we had called more attention to it. Then more recently, there's a follow-up work by Chen, Wang, and Zheng who showed actually purifications don't help when testing any property of rho. So this is like the ultimate purifications don't help sort of lemma. So not just properties of the spectrum, but any property of rho. And the way you prove these purifications don't help lemmas, at least the way that we used to prove them before the random purification channel, you just do it by directly analyzing your algorithm. So you take whatever algorithm that you have that's supposed to be solving your problem, the algorithm that takes in psi ABs, and you'd spend some time analyzing the algorithm, And you'd eventually extract out another algorithm that would work equally well when it's given just psi A instead. So that's different than the random purification channel where you just analyze the input states on their own. You don't bring in the algorithm at all. But if you know to look for it, if you know the random purification channel exists, then it's like very easy to go back to these proofs and see like basically where was it implicitly going on in there. Recently, Angus Lowe actually pointed us to this work of very early work of Hayashi and Matsumoto, which does have actually like a reasonable overlap with this original lemma of myself and Mehdi. Not exactly stated exactly in our form. It doesn't prove quite what we proved, but it has, I'd say, like 70% overlap. So I do think there's a chance that these sorts of ideas were just kind of floating around among like the rep theory crowd of people in quantum information for a while. But I will say I still do not know of a statement of our particular lemma prior to our paper. I'd be interested if anyone else does. Okay, so those were the prior works on these purifications don't help settings. Stream 2 that I'd like to tell you about is something much more recent from a paper of myself, a set of papers of myself and Ewan, and then also Ewan Tang and Mark Jandry, called the acorn trick. And to introduce this to you, let me just tell you a fun fact about acorns. So, acorns come from oak trees, and oak trees, they have these things called mast years on a fairly regular, slightly random, but it's fairly regular. So every, 3 to 5 years or something like that, they'll have a mast year. So what is a mast year? Well, maybe you have an oak tree. In 2024, it will drop an acorn, a few acorns. 2025, maybe again, it will drop a few acorns. And then 2026, it will drop a ton of acorns. This is a mast year. And it turns out these mast years, this phase of mast years, is actually consistent across a region of oak trees. So like in 2024, none of the oak trees produce a lot of acorns. 2025, same thing is true. And then 2026, they're all going to produce lots of acorns together. I guess like the exact reason for this isn't known, but maybe there are hypotheses, one of which is like if you produce so many acorns, like the acorn predators are going to gorge themselves on the acorns, and then like the remaining acorns survive. That's one theory. And one conclusion from these two works, or these three works of mine and Ewan, and then mine, Ewan, and Mark, is that like quantum resources often act like acorns. In the sense that you can often coordinate things among multiple copies of a quantum resource. In other words, like sometimes quantum resources, you can actually take like a base resource and upgrade it in maybe an unexpected way. And oftentimes this upgrading is impossible to do in a deterministic random way. But if you allow yourself to synchronize the randomness across the different instances of your resource, then it is possible. So let me show you two examples that we came across. Example one, let's say you have a state psi. Imagine this as your base resource. And then the upgraded resource that you'd like to get from psi is something called a conditional state. So in a conditional state, you have two branches. The two branches are indexed by the first qubit, so there's a 0 branch and a 1 branch. And on the 0 branch, you just have ket 0, so you just have like a fixed state. And then on a 1 branch, you have your original state psi. So it's a conditional state because conditioned on the 1 branch, you get psi. And sometimes with these conditional states, you also want to pick up a phase. So I'm going to write C sub theta, that's conditional with the phase theta, and that just means on the 1 branch you get phase e to the I theta. There are applications where it's like very nice to have conditional states rather than states. So you might ask, like, given that there are applications where it's useful, can we convert a state to a conditional state? And it turns out that there is indeed no channel that takes in a state psi and then outputs a conditional state. And in this case, outputs a deterministic conditional state, meaning a conditional state where the phase that you get theta is just some fixed phase depending on psi. So there's no channel that does this. It's not too hard to prove. But it turns out you can generate a random conditional state. Pretty easily. So let's look at this. What do I mean by random conditional state? Well, you just want to output, the expectation over theta of the state c theta of psi. So let's look at this. Let's expand this out. So it's expectation over theta. You have like 4 terms. You're going to have the 0, 0, 0, 0 term. You're going to have the 1 psi, 1 psi term. And then you're going to have 2 cross terms. Each of them will be either e to the I theta, 1 psi, 0, 0, or e to the minus I theta, 0, 0, 1 psi. And now when you take the expectation over theta, what's going to happen is it's going to kill off the cross terms. And it's just going to give you 1/2, 0, 0, plus, 1 psi, 1 psi. And this is something that you can easily just prepare with 1 copy of psi. You flip a coin. If it's heads, you output 0, 0. If it's tails, you output 1 psi. Very simple. So that's a proof there. And it's also a fact that given psi tensor n, you can actually use it to generate n copies of a conditional state with a random phase, with that random phase synchronized across all n copies. So this result, it previously showed up in a work of Eli Golden and Mark Zandri. So this is a first example where we thought quantum resources act kind of like acorns. You can synchronize a large amount of randomness across many resources to upgrade them. A second example that we came across, let's say you have a unitary U. Then the thing we want to upgrade U to is something called the controlled unitary. In query complexity, you often want controlled unitaries where you have a control bit 0, or a control bit. If it's 0, you don't apply the unitary. If it's 1, you do apply the unitary. And that's exactly what this is here. You have a control bit. If it's 1, you apply the unitary. And if it's 0, you just do identity. You don't apply the unitary. And this version is a controlled unitary where you also pick up a phase on the 1 branch, e to the I theta. Now, there were prior works which have studied this problem. Given a unitary, can I implement the controlled unitary? And this is the controlization literature. And what they showed is that the answer is just no. You cannot use U to simulate queries to the controlled version of U. But in one of my papers with Ewan, we showed that you can actually do this so long as you're happy with picking up a random phase. So you can actually use n queries to the unitary U to simulate n unitaries to the controlled unitary where the phase is random. Now there's some applications where you care about the phase. You don't want there to be a phase. But there are other applications where you don't care about there being a phase at all. And in those applications, this has turned out to be pretty handy. So in those applications, it's actually allowed us to upgrade quantum query lower bounds that were proven just against unitaries to lower bounds that you can prove against the controlled unitaries as well. Okay, so that's another example of this kind of acorn trick in practice. Later, in this work with Ewan and Mark, we were interested in this last question. Let's say you're given n copies of a mixed state row. Can you use them to simulate access to something called a state preparation unitary, U? And what is a state preparation unitary? Well, it's a unitary U. When you apply it to the all 0 states, what it's going to do is output ket row AB, which is a purification of row. So it's a unitary that you can use to prepare row. That's why it's called a state preparation unitary. And we realized that if it was true that I could use copies of the state to simulate the state preparation unitary, that it would imply that you could actually carry out the simpler task of using copies of row to simulate purifications of row. Because you could simulate U and then just apply it to all zeros, trace out the B register. Or sorry, you just apply it to all zeros and you get a purification. So to answer this harder question, we'd have to answer the easier question of, can we just use rho to simulate its own purification? And we immediately realize this is just like another example of this acorn trick. Like, you want to use you want to take a weaker resource and upgrade it to the stronger resource. Not possible in general, but if you allow yourself randomness, it should be possible. And we also realized, I guess just given our experience with the acorn trick and these knowing these previous purifications don't help lemmas, we realized that basically this acorn trick was kind of embedded in these, under the hood of these previous purifications don't help lemmas. So it's like, once you knew to look for it, it wasn't hard to extract it from these prior works. And I just find, at least for myself, like this acorn trick heuristic, it just proved to be, at least in this project, is very useful way of looking at things. And I'm not sure we would have been able to think of this without like having seen these previous examples. Now, let me also answer this question for you. The answer is yes, actually. It turns out you can use copies of a mixed state to simulate access to copies of state preparation unitary. We showed that you can simulate Q queries to a state preparation unitary U up to error epsilon using order Q squared over epsilon copies of rho. Okay. And also let me point out that Eli and Mark, they had a similar result for the pure state case before this. So one thing actually we're interested in, again, we found this acorn trick thing like useful. It kind of helped us search for a lot of things. And we're like interested, are there other applications? Did we just find the most interesting ones, or are there more interesting versions of the acorn trick out there? We made a lot of conjectures at the end of this paper. Many of them turned out to be false. Some of them turned out to be like half true though. So that was nice, but yeah, just something maybe in the future it'd be cool if this was developed even further. Okay, so that's my own personal history of how we came up with it. Let me conclude just by telling you the outline of this workshop. So 5 more talks, kind of developing applications of this random purification channel to various topics. So today we'll have Jack. He's going to talk after my talk. He's going to talk about quantum state learning. Tomorrow, Marco is going to talk about quantum channel learning. Then Kaon is going to continue with more on quantum channel learning and some tight lower bounds that we're able to prove in these settings. Wednesday, Senri is going to talk about other learning scenarios that are common in quantum mechanics, like bosonic learning. And then we're going to conclude with Eli talking about this random purification channel plus applications to cryptography. So that's all I have to say, so thanks for listening. Any questions? Oh, sure. Yeah, that's a good question. I guess I believe in the math. But I don't know, maybe someone with other people might have other perspectives, since I've, are you raising your hand because you have a thought? Okay, Eli. Yeah. Yeah, I guess there's like, I guess what Eli's going to talk about is like, I don't know if you're familiar with this, and like Fermi and Robert, they have this path recording oracle for simulating random unitaries. That's like an approximate one. You can also do an exact one, and the exact one is like it's not nearly as interpretable, although it kind of is actually, um, but it's like always correct. So the random purification channel is like always correct. Eli is going to tell you something that's like the approximate path recording oracle, where it's like maybe more interpretable. Ryan, you had a question or? Hmm? That's a great question that I actually don't know the answer to. It may not be well defined for. I forget. This is something we looked at, but do you guys remember the answer? Wait, sorry. Can you say that louder? Mm. Yeah. Yes. The Lamy. Yeah. It's only rank D. I think I mentioned there's this paper by Angus and Nora that's coming out today, and I think they're doing a version of the Lamy construction that's also rank R. So that's something to look out for. But yeah, it's like I guess yeah, the random purification channel as is, it's like just not currently well defined for like taking yeah states that have very large dimension and shrinking it down to R. But I do agree it's an interesting question. Any other questions? Oh yeah, I mean, I guess one way of thinking about it is like the random purification channel in the uh, in like the Fourier basis method. What you do is you take rho tensor n and you perform weak Schur sampling. You're gonna get a lambda, and like whenever the lambda has height smaller than r, then you can just carry out the rank R purification. It's just the lambdas that have height bigger than r that you don't know what to do. But like you can use this to sometimes get savings. Yeah. Wait, sorry. Can you speak up a little louder?
So how do you utilize? How can we utilize purification, purified states? Uh, so what kind of how to say it?
Sorry, are you asking like why? Where can we
Yeah,
use a purification? Don't help.
Why still be helpful?
Why does it help to use that lemma, or why the random purification channels?
How can we kind of work around that lemma, and how can we utilize that?
Oh, how can we use purifications? Uh, yeah, it's well, I guess we'll see that like with the random purification lemma, it's like you're gonna wind up doing things that oftentimes like you could have done without purifying, but it's just much conceptually easier to think about them in terms of purifications. So we'll see this in the next talk with like the tomography algorithms that like everything you're going to do there. Again, purifications don't help because you're always starting from rho tensor n. So it's not like you're given a purification. You're always given the original state. But it's just going to be incredibly conceptually helpful to map it to purification. But yeah, just stick around for one talk, and I think it'll be very clear. Chinmay?
I see. Okay. You said at one point that the random purification channel and the optimal cloner channels were similar, and then you said something about they're both some type of general channel. I didn't know what that was.
There's something called the PETS recovery map.
Okay.
Probably there are multiple people here who know what a PETS recovery map is. I'm not one of them.
Pets is someone's name?
Yeah, it's a dude named PETS,
Ah,
and then he came up with a recovery map,
Okay.
and so they call it the PETS recovery map.
Okay.
That is the extent to my knowledge of the PETS recovery map. But I think somehow, I think what it might be is something like when you have a channel that goes in one direction, you might try to create the inverse channel. Is this right? And like maybe the inverse channel isn't always perfectly well defined, and maybe the PETS recovery map is like the best you can do. I don't know. Does anyone know better? Is that right or?
If you have a channel and you want to recover a specific input from the output of the channel, this is a map that does it. And in the other states, it does something else.
I see. I see.
And so in the case of the random purification, we would reconstruct the element, the maximum input.
Hmm. Did you hear that, Chinmay?
Not really. Maybe.
So what Marco said was that if I have a channel and I have like a specific output state and I want to recover a specific input state, then the PETS recovery map is a thing that will allow me to compute that inverse. But it may do like just random stuff on the rest of the space.
So you can invert some projectors in some special ways. Okay.
Yeah, yeah.
Okay. I'll look into it. Thank you.
Any other questions, or is it time to move on maybe? All right, yeah, thanks. Shall I take this?